Hello everybody, and welcome to Ask Math Anything. Just kidding. Actually, today we're going to be talking about problems from the Mustang Math Tournament. If you happen to be a regular subscriber or a regular attendee of our show, you'll be used to the idea that we're going to be talking about all kinds of random math questions that people decided to ask me. Today, we're very pleased to collaborate with Mustang Math Tournament, where they provided some interesting questions for me to think about. This happens to be a math competition, which is organized by students. And the students came up with some interesting problems that they wanted to share with other students from all around their area. If you haven't been here before, I want to welcome you to an hour of kind of unusual mathematics, because what we're going to do is we're going to try to think about interesting things we can talk about that don't happen to be just about one particular lesson. And somebody mentioned, like LMT, that was the Lexington Math Tournament. And when I did a session to collaborate with Lexington Math Tournament, what we did is I spent some time talking about their problems, and then I spent more time talking about their problems, and then I went overtime talking about their problems, and I just kept talking about their problems. And what we're going to do this time is we're going to try to make sure that we spend some time talking about the Mustang Math Tournament problems, and we also have some time open for anyone who wants to ask random questions. And that's what we're going to do. And if you've been here before, I can tell because you made some comment about my haircut. Okay, great. So now this Mustang Math Tournament is something which is it looks like something that's kind of fun. I actually haven't done the problems yet, and that's the entire point. Because what I'm going to do is I'm going to try to show you how someone would think about these problems as you look at them for the first time. Is everyone ready? Let's go and see what they had in mind. For the first question, we have this. Oh, wow, they like puns. The unbridled approximation round is an estimation round where the closer you are to the exact answer, the more points it is worth. No calculators or other aids are allowed during the competition. Okay, so this is a problem where they're just looking for us to approximate. And I guess you're going to see me attempt to approximate the answer to this question. Approximation means that we're not looking for the exact right answer. For that, you can use Wolfram Alpha. Instead, the question is, how close could we get? And look at this. Rithik thinks this is cool. I think this is cool too. You're just trying to get as close as you can, and you get more points the closer you are. How many digits does 3 to the power 87 have? Now, what might I use to do this? So I'm going to tell you a few things that come to mind. If I do 3 to the power 87, 3 is not really close to 10, so I don't want to use that. But I could take 3 squared. Let's go and look at some powers of 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th is 81. Are any of these interesting? It's not entirely clear how useful some of these things are, but that 3 squared is 9 is somewhat useful. For the 3 squared is 9, I could say that 3 to the power 87 is equal to 9 to the power 87 divided by 2. And 87 divided by 2 is 43 and a half. Does that make sense to people? So if I have 9 to the power 43 and a half, okay, here's a pretty bad approximation, but I could say this is approximately 10 to the power 43 and a half. Is that a good approximation or a bad approximation? Well, if I did 10 to the power 43 and a half, I would say that is a number which is 10 and 43 and a half zeros afterwards. And so I'd guess, I went from 9 to 10, so it should be a bit less. Right here, what I would guess is I would guess that we have 43 digits, right? I'll guess that this is 43 digits. So I would guess it's a 43-digit number. And this is an estimation round, so we just try to get as close as we can. What's the right answer? Oh, it looks like people... What is the answer, actually? I'm a little bit curious. It's estimation round, so estimation, we don't have an exact answer. What do we have? 42? Is it really 42? 40? Wrong answer. Yes, my assistant tells me it's the wrong answer, which is correct. It is the wrong answer. But what is the answer? The question is, how close can we get? I see lots and lots of people saying 42, but it's not clear to me whether you actually know it's 42 because you checked it, or because 42 is the answer to everything. Aha! Now Luke Wang says it's 3 point something times 10 to the power 41. So 42 is the actual answer. Not bad. So this was completely with just estimation. And you're right. Somehow it's hard to do this thing properly if you don't actually have a calculator. But okay, so we could do this. If you're curious, what I was trying to do here is I was curious if there was another power of 3 that was closer to a power of 10. And I didn't find one. Okay, let's go to the next question. I'm curious what the next question says. Oh, more approximations. And this is now question number 10. This must be hard. And don't type the answer into the chat because I don't want anyone to tell me what it is. Okay, so we're supposed to get as close as we can, and we can't use calculators. And we need to do square root 17 plus square root 11 to the power 6. So what would I think about here? So square root of 17 is a little bit more than the square root of 16. Square root of 11 is a little bit more than the square root of 9. But neither of those is giving me something that I really like. The next thing I would be curious is, are 17 and 11 nicely positioned with compared to any other numbers? Not really. So I guess if I'm looking at this, I guess the thing I would feel like doing is I'd first feel like squaring it, because I can at least get somewhere with that and see what that is. So let's square it first. Root 17 plus root 11 squared is 17 plus 2 square root of 17 times 11, which is, that's how you do 17 times 11. You write 1, 7, and you put 1 plus 7 in the middle, plus 11. And so this is equal to 17 plus 11 is 28 plus 2 square root of 187. I'm supposed to take that cubed. Do I actually want to or not? Looking at this, I'm basically trying to think to see, is there anything clever I can do with these particular numbers? And square root of 187, right? What squares do I know? I know that 13 squared is 169, and 14 squared is 196. So this is actually quite close to the 14. Oh, that's interesting. So it's almost like 28 plus 2 times 14. It's almost like 56. Okay, so I'm going to say right now, this is approximately 28 plus 2 times 14. And 14 times 2 is 28, so that's about 56. It's a bit less than that. It's a bit less than 56. And if I wanted to just approximate, I would say 56, and that's about 55. 55 is more fun to cube, because if I have it squared so far, now I need to cube it. So now I just am curious, what is 55 cubed? 55 cubed is equal to 5 cubed times 11 cubed. And I happen to know what 11 cubed is. It's 1331. Oh, but that's not going to be as efficient. It'll be more efficient to do the multiplication this way. When you want 55 cubed, it's 55 times 55 squared happens to be 5 times 6 is 30, 25. So when you multiply something ending in 5 by itself, you take that digit before the 5 and multiply it by the next digit. That's what happened here. And so let's see, what is this? 3025 times 55. 5 times 5 is 25. 5 times 2 is 10, plus 2 is 12, hopefully. And then 1, 5. Oh, and I write the same thing again. The reason I wanted to multiply by 55 is I just have to write the same number twice. 3, 6, 6, 1. Okay, 1, 6, 6, 3, 7, 5. So that would be my estimate. How close are we? I'm actually a little curious. So I expect this to be the wrong answer, but I'm curious how close we got to the right answer with this. Real answer, 169567. Okay, not too bad. You know, like this is an approximation problem. And so, you know, are we going to get the exact answer? We're not expecting to. But the question was, how close can we get? Seems pretty close. But I wanted you to see how I did this. I didn't want to first go and figure out what these were and then take the sixth power. That's dangerous, because then you might have a mistake already. You might have made a mistake in your approximation. On the other hand, once you do one time of squaring it, the numbers aren't terrible, and then you can go and take your square root and find the thing that's closest to it. So that's where we are. So that was question number 10. What question are we on? Let's find out. What's next? We are now in the Gallop Round. I guess the Gallop Round means we're not supposed to estimate anymore. Now we need to find the right answer. So this is question number 19. quadrilateral ABCD is constructed such that BD bisects angle ABC. I wonder what that looks like. Oh, like this. Okay, so we have this particular quadrilateral ABCD that's got those 4 points, okay? It's a quadrilateral. There should be one more line here, but that doesn't matter. And BD is going to bisect angle ABC. Oh, that's what these equal angles mean. So these two are equal angles, okay? Next, X is the intersection of AC and BD. I guess that would be right here. That's X. And we have that AB equals 4. So we have 4 here. We also have BC equals 8. That's 8. And then this thing happens to be also 4. BX is XD. Oh, wow. All these things are 4. That's kind of cute. And I have AC is equal to 6 root 2. So there's something going all the way across here, which is 6 root 2. And I'm supposed to finally find CD squared. Okay. So if I look at something like this, I guess my first instinct is to say, what in the world can we do? We have some information, but we didn't write down all the information. So let's write down one more piece. 6 root 2. I like to do something like this to write across so that I know it's the entire thing. This is AC. And I also like to remind myself what I'm looking for. I'm looking for CD. Now, what kind of techniques could I have? Before I do a lot of calculations, I want to have some hope that this might actually be what I need in order to finish this problem. You see, when I look at this problem, I see an angle bisector. If there's an angle bisector, there's something called the angle bisector theorem. And the angle bisector theorem says the ratio of this part to that part is the same as the ratio of this to this. I don't have time to prove that here in this particular lesson because that's more for an entire course. However, in this thing, we can go ahead and use this. Actually, we did this in our online geometry course already. And the ratio is nice. 4 is to 8, right? So if 4 is to 8 as this piece is to that piece, that's like 1 is to 2. So this is 1/3 and this is 2/3. And if that was 6 root 2, now I can label 1/3 of 6 root 2 is 2 root 2. And 2/3 of 6 root 2 is 4 root 2. And now I'll erase the 6 root 2. Okay. Now, next thing I wonder is, do I have enough information that I could figure this thing out? And the answer is yes, because if I was interested, I could actually draw this particular triangle. I could also draw that particular triangle, and I could just take that and go over there, and that would be defined, right? So now if I know that that's defined, the next thing I'm curious about is there anything here that's fun from any kind of a symmetry point of view? I'm always a little bit afraid if the question is drawn to scale or not drawn to scale. And when I look at that, I'm trying to think, is this problem drawn to scale or not? Because it looks awfully like the answer would be, that it's the same. But oftentimes these problems are not drawn to scale. And when I say the same, it's like, gee, it looks pretty isosceles. But I'm not willing to believe that yet. That might be too good to be true. Okay. So don't tell me how to do this yet, because I'm still thinking about this, right? If I'm looking at this, it's like, is there any reason in the world why I would be able to control those angles? Oh, wow, I see something neat. So I'm going to do something where I'm following some angles around. So I see isosceles triangles. I'm going to do a technique called angle chasing, okay? This angle equals that angle. You know why? It's because both of them have a 4 and a 4, all right? So if I've got the 4 and the 4, those two angles have to be the same. That's like base angles of an isosceles triangle. I see another isosceles triangle. I wonder if it's useful. I see this is an 8 and an 8. So if that's an 8 and an 8, let's mark 2 more angles that are the same. This is equal to this. Could that be useful somehow? That's not immediately obvious yet, whether that's useful. Oh, but there's something else. I have similar triangles. Maybe that's what this is about. You see, this angle up here is the same as that angle over there. If I have, like an isosceles triangle that's coming out, and it has the same top angle, then that means that this is just double. Bam, that's the answer, okay? So what we have here is that this triangle, all right, is actually similar to this triangle because they have the same angle on top. They have the same angle on top. They're both isosceles, and it's just like this was 4, and then that went to 8. So it went by times 2. That's it. So actually, the answer should just be 2 times the 2 root 2. So this is equal to double of 2 root 2, which is 4 root 2. And let's try. Let me ask my assistant. We're good. That's the right answer. Okay, so that's how we do this problem. Whenever I look at these things, I'm just lazy, okay? There are ways to do this where you just beat the problem up. In fact, you can sometimes use what's called trigonometry. You could actually figure, oh no, that's the wrong answer. CD squared. I didn't read the question correctly. That is the most dangerous thing to do. It's to get so excited that you got the answer right that you didn't read the question properly. So in that case, this is wrong. The question asked, what is CD squared? And CD squared is 4 root 2 times 4 root 2, which is equal to 4 times 4 is 16, times 2 is 32. Thankfully, we have a large YouTube audience here, and everyone's been helping to watch to make sure that we don't make these kinds of mistakes. So thank you, audience. So I got this one wrong. Ouch, facepalm is correct. But as you can see, this is what actually happens. You get so excited that this was supposed to be a hard problem that you're like, I got it. And then you find out that you read the problem wrong. Oops. Anyway, now we know how easy it is to make that kind of mistake. But the thing I was trying to say here was that, oh yeah, exactly. CDX is isosceles, so this is actually isosceles. It's true. It's also isosceles because it's 4 root 2 and 4 root 2. That's cool. The Mustang Math Tournament people found some pretty interesting problem. I like it. So it's a nice question. And you also can see I didn't want to use the trigonometry. I just wanted to go and say, is there a way a lazy person could solve this problem? And always I try to be lazy first, and only after I am not able to solve it in the lazy way, then I'll do it with the brute force. What are we doing? We have a question by Andy Jia. I don't know. Let's find out what the next question is. Oh my, lots of words. Okay. Oh, I know. I was having trouble reading this stuff because it was too far away. Now it's nice and big. I just zoomed it in. In a world where words are associated with values based on the multiplication of each letter. Oh no, you want to multiply? I'm used to adding. Each letter is an algebraic variable. You are told 1 is 1, 2 is 2. I get it. Okay, multiplication of their letters. Oh, neat. So this is saying that somehow O times N times E is 1. T times W times O is 2. S times I times X is 6. Whoa, this is really interesting. Okay, I'm curious. I didn't even know this was possible. I didn't even know it was possible to go and have 26 letters, each of them representing a value. And then when you go and multiply things together, the thing would work. Now when I look at this, I say, how in the world can you try to do this? Well, each number is a numerical quantity. We don't know for sure that they are integers. In fact, I would be pretty sure that they're probably not integers. Unless it's possible to go and do it with them all being integers. Let's see. If we look at this, sometimes the hope is that you can have like most of them be 1. The hope would be that most of the values are 1. And if most of the values are 1, and you just use a few of these other letters to be worth something else, then you would be able to have things that are worth more. Then you'll be able to figure out what each thing is worth. I also see people are having a lot of fun thinking about this. It's like if you could make the word 20 by just putting together some letters from these actual words, that would be great too. Oh, I wonder if we can do that. That might save us a lot of time. So how might I make 20? So if I want to make 20, I need something which has ty inside it. Ty is like thank you. Is there anything inside here that might have a ty inside it that's convenient? Well, 90 is quite nice. How do 90 and 20 compare? If I have 90 and I have 20, so this thing, nety, is this thing, nety. Okay, so I seem to want to know what is tw. Basically, I want to know what is tw over ni, and I would multiply 90 by this. How do I get tw over ni? Oh, that's interesting. Maybe we could actually do this, because tw is like part of 2, and ni. Oh, okay, this is kind of neat. Actually, I see some people are also helping to think about this. Oh, yes. Thank you. We have an audience here. The audience is so sharp. We can actually use this idea to start to figure out what these little pieces are. So for example, from 6 to 6t, the 6 and then the ty is going to give you a 10. Actually, that's a useful idea too. So because of the 6 and the 6t, because I go from 6 to 60, this ty is equal to 10. Ty, audience. Okay, what else can we do? So then I need to know what is TWEN. How could we try to get TWEN out of something? So TWEN, that would again be the TW comes from 2. Where else is W? Oh, that's something else to know. The W in all of these only comes from the 2. So we actually will need to use that somewhere. Okay? So we wish we knew what was TWEN. I know what TWO is. So I need to use the TWO to get the TW. Is there anything else I can put together? Oh, wait, here's 8, and there's AT. We just found out that the Y. Oh, wait a second. The 8 to the 80. Look at that. The 8 to the 80 was times 10. That tells you that the Y is 10. Okay, so the 8 is 8, 80 is 80. Okay, so this works. I also just realized, now I understand why it's echoing. The reason it's echoing is because I have a speaker over there. I was just wondering why all of a sudden this room was echoing. Okay, right. So there's 8 going to 80. That's by times 10. So the Y is 10 and the T is 1. This could be useful. Hey, this is a fun problem. So the T is 1. That's because I went from 8 to 80. And there's 7 to 70. Okay, that's fine. 9 to 90. Okay. So actually, I only need to know what is WE. How might I find what is WE? Let's see. So W times O. Oh, yeah. T is 1. So if T is 1, W times O is 2. That seems useful. T is 1 now. So WO is 2. Oh, and here is the EN. EN is 10 because T is 1, right? So I have here EN is 10 because T is 1. So T is 1. So this is telling me that EN is equal to 10. Okay, so now I can look at this piece. What do I have? So I have my TY. TY is already going to be 10. This T is 1. And my EN is a 10. Now I just need to know what is W, right? Because the EN is going to be the 10. And then there's a 10. And okay, there's a 1. So what's the W? I just need W. So I have W times O equals 2. Are there any other ways that I could get rid of the O, right? At this point, this is the problem solving. The problem solving is I just need to get rid of the O. And where else is there an O? There's an O over here. Oh, is there anything I can do with the EN? Hey, the EN is 10. Aha. So if the EN is 10, now we know what O is, because O times 10 is 1. So O is 0.1. And if O is 0.1, now the W is 2 divided by 0.1, and that happens to be 20. Okay, so then W is 20. Then I get that this W is 20. Okay, so now that the W is 20, we can put everything together. The W is 20. And when we multiply, we get 20 times 10 times 10, and the answer looks like it is 2,000. And are we good? It's correct. My assistant says it's correct. Great. Really fun question. I will say, you guys who thought of this, you are pretty creative. I have seen a lot of different questions before, but I've never seen something quite like this. I didn't even know this was possible. Good for you. Actually, I'm going to ask my assistant to help me with something else right now. Would you be willing to refocus the camera? Because we were actually just using the camera earlier today, right here in the studio, to film something else. The refocus is the ring that's on the far outside, as you remember. The refocus is the ring that's closest to the lens. The ring that's closest to the lens. The closest to the lens. There are 2 rings, right? And if you move that, then you should see the red dots come. Great. So thankfully, we have an assistant in this room because we were just adjusting, we were just filming something else earlier today. And so now we will have something which is more sharp, and hopefully it's even clearer for all of you. Hey, I really like this question. Good for you. Good for you. I'm impressed. Okay, what else do we have here? Let's go to the next problem. I wonder what we're going to see. You didn't see a difference, says AC. Well, that's probably because you guys are watching from YouTube, but we actually record everything here and we keep it. And when we record everything to keep it, we also want to make sure that we have something that's as precise as possible. All right. Next. Ooh, what's this about? You guys are giving me some hard questions here. Using standard operations, addition, subtraction, multiplication, division, parentheses, and exponentiation, determine the minimum number of 3's needed to construct 2020. Remember that you can only use 3's, and you may not string together multiple 3's to form larger numbers like 33. Oh wow, these are hard. Okay, whenever I see a question like this, I'm worried that somehow, I'll find some way to do it, and then maybe it won't be the most efficient. So let's start to try. The first thing is just to find some way to get 2020. And since we're greedy, we will probably want to use exponentiation as much as we can. So let's try. If I do 3 to the power 3, I'm curious what the powers of 3 are, how close we can get to 2020 with powers of 3, because that's the most... Oh, you can also use powers of 6, or we can use other kinds of powers too. But in general, the best you can do with numbers is to go and make the power as big as possible. So let's look at some powers of 3. We just saw some powers of 3. We saw up to 3 to the power 4 was 81. 3 to the power 5 was 243. And 3 to the power 6 is 3 times that. What's that? 3 times 3 is 9. 3 times 4, oh yeah, I know this one, 729. Then 3 to the power 7. That's equal to, 3 to 7 is 9 times 3 is 27. 9 times 2 plus 2 is 9. Is that right? No. 3 times, no, that wasn't right. It's 3 times. 3 times 9 is 27. 3 times 2 is 6. Plus 2 is 8. And then 2187. Oh, that looks pretty close to 2020 already. I'm going to try to do a few things. I'm just going to first try to make something with a few 3's, and then we'll try to do better. Okay? So if I go to 2187, how many more 3's do I need? How much more do I need to go to get to 2020? 2020 minus 2187 is equal to 10 minus 7 is 3, 12 minus 8 is 4, 43. And I'll believe that because 87 is... No, that's not right. This is how I'm checking, right? 87 is 13 away. Whoa, really? 33? That feels kind of lucky. You told me I'm not allowed to make 33 though, which is not fun. Not that it's not fun, it's just like that's what makes this question interesting. So now we see that we could try to make it. Here's one way, okay? Let's make 2187 and then add 33. And that would just be one way to do it. How many 3's will we use? If we want to do 2187 plus 33, I'm not saying this is the answer, we'll try to do better. It's 3 to the power 7. 7 is equal to 3 plus 3 plus 3 divided by 3. No, that's not as efficient. So that's 3 to the power 7, by the way. But there's another way to get that. There's a better way to get 3 to the power 7. It's 3 times 3 to the power 3 plus 3. So I saved 1 3 that way. That's 3 to the 7. And then plus 33. What's 33? 33 is 3 cubed, which is 27, plus 27 plus 6. Now, this is one way I could do this. But I'm not saying this is the best answer. How many do I have so far? I have 1, 2, 3, 4, 5, 6, 7, 8. Right? So here I have 8 3's. But now the question is, what else can we do? Because we want to get better than this. Okay? This is just what you do first. We can do it with 8 3's. We can use parentheses also. And we can use exponentiation and all of these different things. What else could we do? We want to make 2020. You can see that I'm thinking. I'm trying to say, is there something that's more efficient, right? Because I can get to this huge power of 3. I can get this huge power of 3. Oh, just a second. So let's see. Stop. I did wrong subtraction. Oh, I did wrong subtraction. Let's see. Oh, let's see. So it's good that we've got people here. So 3, is 2187 wrong or is 2187? Oh, subtracted wrong. That would be what's wrong. So let's see. 10 minus 7 is 3. 11 minus 8. Oh, wait. What? It goes the other way around. You can't subtract that way. Subtraction is wrong. Oops. Okay, let's stop with this. That's not right. We're supposed to subtract the other way. So it goes the other way. And as you can see with these kinds of things, we want to go and find out, how you could try to get a better answer. And the first way to get a better answer is to not subtract wrong. Thank you, everybody in the chat. No wonder you're trying to say that. So 2187 minus the 2020, right? When you subtract, you get 7, 6, 1. Oh, But that's not pleasant. So I need to do 3 to the power 7 minus 167. So this also doesn't look so good. 167, oof, yeah. 180, how would I get 167 by using just 3s? If I'm thinking about this, I'm like, 169 is something squared, but that's not going to be very useful because I want to get things with 3s inside them. If I get a 2 somehow, that doesn't seem very good either. So 167 doesn't look very good. What else could I do with the 729? I guess that's a question. Well, it's not that it's that bad. It's that somehow, if I do 167, I'm basically saying I could get 169 minus a 2, but that's actually not nice either. And if I go and take 81, 81 times 81 happens to be 81 plus 81 happens to be 162, but then I still have to add 5. So that's still not nice. Let's see. Find the closest multiple of 3 and then add or subtract 3 over 3. Yeah, you're right. I could try to do something like that too. Does that work? 168 happens to be a multiple of 3. What's 168 divided by 3? Let's find out. So what's 168 divided by 3? 168 divided by 3. This is how I do the scratch work. 3 times 5 is 15. Subtract 18. 3 times 6 is 18. But that's not very good either. So 56 is not going to be fun. So 56 is not going to give us that much advantage. So to me, it's like, okay, let's just make one way first, which has a ton of 3s inside it. I would make the 81. 81 is 3 to the power 4. That's neat. I wonder if I can use parentheses here. So if I want 3 to the power 4, so here's what I want. I want 3 to the power 4 times 2. So I want 3 to the 4 plus 3 to the 4 plus 3 to the 7. You see where I'm going with this? 3 to the 4 plus 3 to the 4 plus 3 to the 7. That's 162 so far. I need to add 5. And I need to add 5. What's 5? 5 is like 5. But I could write it as 3 plus 3 over 3 plus 3 over 3. So far, this thing here happens to be the 3 to 7, which is this, plus the 81, plus another 81, that gets you to 162, plus 5. Now here's what I'm doing. The reason I took all this out is because I have a way of parenthesizing. This is equal to 3 times 3 cubed plus 3 cubed plus 3 to the 3 plus 3 plus, close parentheses, plus 3 plus 3 over 3 plus 3 over 3. I can improve the last part. Let's make it 6 minus 1 is 5. That's with a minus sign. Plus 3 minus 3 over 3. So what do I have now? Let's just take a look at this and see. Does this actually help me at all? If you subtract instead, does this give us anywhere? Does this get us anywhere? First of all, is this correct, or did I make another terrible, terrible mistake? Maybe I've made another terrible mistake. Oh, subtract! Why am I adding? No, these should be subtracting. Yeah, these things are subtracting. Yes, that's right. I was adding. These should all be subtracting. Let's flip it around. But my parenthesization will still work, all right? Let's do this again. As you can see, the signs are backwards, and this is the same mistake I made the first time. I want 3 to the power 7 minus 3 to the power 4 minus 3 to the power 4, and that's subtracting 162 so far. Now, in order to subtract, I'll subtract too much, and then I'll add back 1. Does that make sense? So now it should be good. Now hopefully I haven't made an arithmetic error. 2187 minus 167. Okay? Now, what I'll do is I'm going to go and I'll factorize this. 3 times 3 to the 6, which is 3 to the 3 plus 3, minus 3 to the 3, minus 3 to the 3, and then minus a 3, minus a 3, plus 3 over 3. At this point, my hope is that this is actually 2020 without having made some terrible, terrible mistake. I see. Somebody said I need a banana. That's correct. I do need a banana. Let's get this thing doing better. But at this point, we have this like pluses and minuses. The signs should be correct. How many threes do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I can do this with 12 threes. Now let's see. Can we be greedy? Could we do anything better than 12 threes? Factor 3 cubed out. Oh. That's an interesting idea, but if you factor 3 cubed out, I'm going to get 1s over here, and 1 is not allowed. And indeed, one question is like, is there a better way? Oh, you said I can't use fractions. It's true I can't use fractions, but I can use division. So if I want to use division, I could say plus 3, like divide 3, and then that would work too. It actually says we can't use, it doesn't say we can use factorials. So we only get plus, minus, times, divide, parentheses, and exponentiation. Do we believe that we can do any better than 12 is the question now. So why no factorials, asks a person who has the username of Weirdo. It turns out that somehow, unfortunately, we aren't given factorials, so we can't use that, right? So the factorials aren't here. So somebody suggests instead of factoring 3 out, factor 3 cubed out. Let's try that. Maybe that's actually going to help us out. Thank you very much for being in the chat. As you can see, what we're doing here is we're watching how I attempt to solve these, while everyone here helps to give us more hints to solve this properly. I want a longer pink and purple line. Let's go all the way up here. Nice idea, factor 3 cubed out instead. If I factor 3 cubed out, then I get 3 to the 4th, which is 3 times 3 cubed, and then plus, so minus 3, minus 3. That's the first part now. Okay, so that's my first part. Factor 3 cubed out instead. And then I get minus 3 plus 3 over 3. Now suppose that's what we did. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ah, we have 11 of them. So this got better. All right. Is there anything else that we can do? Can we cut this down any further? If I'm looking at this, I'm going to say when you happen to have the 2187, which is 3 to the power 7, really the only thing you can do is try to factor things out. So I'll say, with this particular one, it doesn't look like we can do much better, although we would never know. At this point, I'm just going to I'll ask our assistant, is the answer actually 11, or is there an even better way? Because these kinds of questions are very, very hard. Wow, it's the correct answer. So our assistant has said the correct answer is 11. So this is in fact the best way. But the credit for getting this correct definitely is not me. The credit for getting this correct is all of you who are watching this live stream who also like bananas, which is excellent. So thank you everyone on the live stream for first of all correcting my arithmetic mistakes, but also for actually coming up with all these ideas together. I think my goal was to show how you can start to use the factoring to go and save some of the work. But then ultimately, the better idea came from the audience to factor out 3 cubed instead. Well said. Okay, what else do we have? Ooh, equilateral triangle. An equilateral triangle with vertices 1 plus root 3, 0. I guess that's 1 plus root 3, 0. And 1, 1. And 1 minus 1 is rotated around the origin by 90 degrees. It doesn't say what direction, but I guess it doesn't really matter. If the area swept out by the figure can be expressed as pi a plus b all over 4, where a and b are real numbers, compute 2a minus b. Well, I'll try not to make the same mistake again this time and just get excited about having the answer. What happens if you rotate a triangular thing around the origin? I wonder if there's another picture with more space. There is. When I want to do this, I'll start to rotate different parts of this around the origin. And if I do that, let's see. So this point is going to go here. That's the center. And what else will happen? By the way, that's the point that's closest to the origin. So I'm going to get something which looks like this shape, and that's the closest part to the origin. And then it's going to make another shape on the other side. Oh, I need to know what these are. These are 1, 1 and minus 1, 1. Okay. So it's an equilateral triangle. Oh, that's neat. If it's an equilateral triangle, then it's going to go across to here. Okay. All the way over to this. And then we'll get an equilateral triangle. It goes up to about here. Okay. And this is what we're seeing in the internal shape. It's like this, right? So the part that's closest to the origin is this point. And now what part is the farthest from the origin? It's obviously here. So the farthest part from the origin is going to also move in this kind of a circle. Okay, so now I think that the shape is going to really just be this. I'm trying to imagine what happens to every other point as we rotate. Like this point here, as you start rotating, it's just going to start moving inside. Okay, that's going to move inside. This is going to move inside also. And then this thing here can also move in. Ooh, what happens when this one moves? Wait a second. When this one moves, it's going to rotate 90 degrees, and it's going to rotate up to here, right? It's going to rotate up to here. So I think what we've got is I think we've actually gone and drawn this entire shape that we're going to get. We just need to find the area of this shape. Is that okay with people? We just need the area of this shape where it's going to go like there's this little bit sticking out here, and it'll go to the little bit sticking out there. Okay. Oh, I think I know how we can try to do this. But I thought the question would need a square root inside it. We'll find out. I thought there would be a square root in the answer if this is actually the area. You see, because if I look at this, what I see is that there's two bits which are sticking out, which are two halves of the equilateral triangle. There's this part sticking out, and there's also this part sticking out. And apart from that, it's just going to be a segment of the circle. So it's a segment of a quarter circle, right? It's like a quarter circle minus another quarter circle plus two of these things. But the thing that's making me wonder a little bit is that the problem said that we are supposed to compute this thing, and we get 2a minus b. Is that a whole number then? Let's find out. Well, you're telling me that the vertices are 1 plus root 3, 0, and 1, 1. So you're telling me that the height is root 3. That height is root 3. And this base over here this is 1, and this is also 1. So if that's the case, the area of the entire triangle is half base times height, which is 1 times root 3. Area of the triangle is just root 3. So the area of the whole triangle is equal to root 3. Well, if that's the case, then what can I do? Let's go and take a look at this. If the area of the whole triangle is root 3, looks to me like what's going on is that we're just going to take half the triangle plus the other half of the triangle plus this like quarter circle thing. Before we go on, let's double check and see if that's really the shape. That looks like the shape. Okay, so now I have this part, which is the outside. The yellow part is root 3. So my answer, my area, is equal to root 3 plus, now I have this blue part, which is inside. The blue part is going to have some pi inside it. And so it's going from 1 to 1 plus root 3. And we're doing a quarter of a circle. So I'll do it this way. It's a quarter of, as if it was the whole circle with the big radius, which is 1 plus root 3 squared, minus if it was just the one thing inside, 1 squared. Okay? So this would be like pi times the big radius squared minus pi times the little radius squared. All right? So what do we have? We just need to go and simplify this thing inside. Oh, there's a pi. Forgot the pi. It's 1/4 pi r squared. So I'll make the pi right there. Okay? And if I do that, let's just go and try to simplify this. I have square root 3. Actually, let me make sure I read the question right, because something about this is a and b are real numbers. I guess so. I'm just wondering why the question asks for 2a minus b. But I guess we could do that anyway. Let's see. This is going to be root 3 plus pi over 4 times 1 plus root 3 is 1 plus 2 root 3 plus root 3 squared minus 1. Okay, and at that point, this is equal to root 3 plus pi over 4 times 3 plus 2 root 3. Okay, I guess we're trying to put everything together. So if we're putting everything together, then this is going to be all over 4 pi times 3 plus 2 root 3 plus 4 root 3. So that's what's going on. I was wondering where this root 3 was going to go, because the problem I was going to be like, the answer is going to have a root 3 in it, except that the problem asked, what is 2a minus b? 2a minus b. So a is this one. And b is this one. So now I just need to know what is 2a minus b. I was so worried with the root 3. I was like, I must clearly have a mistake somewhere in here, because there's no way that the problem answer has a weird root 3 in it and you ask me for 2a minus b. But now that I see that the 2a minus b will cancel out the root 3, 2a minus b is just 2 times 3, which is 6. 2a minus b is equal to 2 times 3, 6. That looks like a b, but it's a 6. And I'm going to propose an answer of 6. And my assistant says it's the correct answer. So that actually shows that that happens to be the answer to this problem. The answer is 3 factorial, or 3 plus 3, however you want. Yes, Willow the Pillow, all these creative high schoolers, that is the right way to think about this. These people are really creative. I actually thought that I was doing the problem wrong because somehow I thought the number wouldn't work out. But wow, it just worked out. They made the whole thing cancel. You guys are pretty sharp. Okay, now we only have 15 minutes left, so what I want to do is I want to make sure that there is some time for me to answer any kind of questions that might come. These are kind of fun, says Harry Liu. You're right. This is why I like to play with the questions that people propose. And as you can see from today's thing, I need to eat more bananas. I mean, you can see that somehow it's very, very possible to get these kinds of questions wrong. That's what happens in real life. And furthermore, you can also see that when you bring 250 plus people together to go and try to solve problems together, it can really be quite fun because the kinds of answers that come can help us solve the problems correctly. I can't believe that we actually got that previous question right about the smallest number of 3s. Whenever I see a question like that, the thing in my head is, there's no way I'm going to get the right answer because I'll come up with something and it won't be that efficient. Okay, we have 15 minutes left. Let's go and take random Q&A. So, and actually, if you're here from the Mustang Math Tournament and you somehow managed to watch this channel, this last part is actually what we usually do. And what we usually do is we use this time to answer any kinds of questions that people will have. All right, what kind of questions do we have here? I see that Lucas Wu said, this is so cool. I'm not sure if that's a question, but I'll take that as a question while I take a sip of water. Ooh, I see a good one. Luke Wang, why is root 2 so useful? Well, the reason it's so useful is because it's the first number you get that's not a rational number. I'm drawing this funny triangle in my hands. You know, like, we're going to skip past all of these. We didn't actually have time to do all of the questions that people had. Oh no, now you can even see what some of the questions that they were going to do were, but we should be able to get past all of these slides. No, we can't. Oh no, I wanted to have a blank thing, so we're going to go back. So I had actually wanted to have a blank screen. We'll just draw it over here, okay? So as you can see, they've got some pretty interesting questions. I recommend that you check out their questions afterwards if you found this interesting. But you asked about root 2, right? So root 2 is something where you can get a root 2 very easily with just 1 and 1. And boom, square root 2 appears. That's actually why square root 2 is so useful. It's the first one that comes. And you'll see it a lot whenever you're doing these geometry problems, because this also happens to be the 45, 45, 90 right triangle. And you can see there's something about rising plus virus equals corona. Gee, they have some really interesting questions inside here. I see some people want a studio tour. Again, I haven't set that up yet, so we don't quite have a way to do that. I would basically need a second camera set up. But we'll keep making the studio more fancy, so we can hopefully get there. I see some people are asking whether the assistant can do a face reveal. That's entirely up to the assistant, and at this point, the assistant hasn't said yes. So that will be a separate topic. I'm happy to go and show up in front of the camera as much as we want. But the way we always operate is that anyone else who's helping in the studio, whether they go in front of camera or not, that's their choice. Oh, AC asked, what was your lowest grade in high school? 9. Oh, is that not the question you asked? My lowest grade in high school was 9. I guess that was not what you were hoping for the answer. Yes, that's a grade, Skylar. It's totally a grade. Haven't you heard of 9th grade? Okay. Yes. I think somehow people were wondering about other kinds of grades. Yeah, 9 out of what? 9 out of 12. Come on, everyone. My lowest grade in high school was 9 out of 12. Okay, we won't continue talking about this. I do believe, yes, it's good to get good grades, do well in your classes, and you can actually get decent grades. Just work hard. Let's see, what else can we do? The answer I wanted to give you was 9 out of 12. Okay. What other questions can we have? Oh. Let's see. I'm looking at all of these to try to see whether there's something that we can do that's with mathematics, that we can do something. I'm basically looking through all these questions, trying to find something that I can hit on which has math inside it. 9 out of 12 is actually not really that high. That's correct. That's a C. What else do we have? I actually see somebody has asked, saying, it would be really cool to try to reattempt the second problem algebraically. I'm curious what that means. Let's go back and look at this. That requires that we know what was the second problem. So let's go all the way here. I'm going to call this the first problem. And this is the second problem. You want me to attempt this algebraically? What would that mean? So I guess I don't understand the question. The question is saying, reattempt this algebraically. But if you say that there's a way to reattempt this algebraically, then I get kind of curious. Is there something behind this problem where we can do a better job? Binomial theorem? You know, like we could try to use the binomial theorem, but then I need to do all kinds of like these things to various powers. So that doesn't sound like fun. I could try to factor out a root 11. Let's try that. Hey, let's try another way, okay? I'm going to try another way. I want to factor out square root 11. And if I factor out square root 11, what happens? This is square root of 11 times, ugh, that's disgusting, times the square root of 17 divided by 11 plus 1. And then that whole thing to the power 6. The reason I'm willing to do this is because square root 11 to the power 6 is not bad. Square root 11 to the power 6 is 11 cubed. And then I need to do this. 1 plus the square root of 17 over 11 to the power 6. Now I'm curious, what is 17 over 11? Is that going to be nice? I'm not sure. Let's try to divide. I'm just curious what 17 over 11 is. 17 over 11 is 1 plus 6 over 11. Is that nice? I'm trying to think of it as a decimal. 1 plus 6 over 11, which is 1 plus, 6 times 9 is 54, over 11 times 9 is 99. You see what I'm trying to do? I'm trying to get 1.54 repeating. Now is that nice? Let's see. So if I use that as an approximation, then I would say this is approximately 11 cubed times square root of that. 1 plus, oh no, do I want to take the square root of 1.54? That's between like 1.44 and 1.69. In fact, it's almost halfway in between. 1.44 is 12 squared. So I might actually call this 1.25 to the 6. And the reason I did that is I said, 1.2 squared is 1.44, 1.3 squared is 1.69. So this is like halfway in between. Do I actually want to do this though? It doesn't look like it's actually very pretty. 11 cubed times 2.25 to the power 6. If I was to do that, I would get, just like I would be able to do some multiplication and maybe I would be able to get some answer, but it's not clear to me that this is a better way to approach this question. So I'm not actually going to go further on this one. I'll just simply say, I'm not entirely sure what you mean by doing this thing with algebraic approach, but I think that this is definitely one way that you could have tried to do this. Yes, indeed. This is some nice power. 2.25 is 15 squared, 1.5 squared. So it's like 3 over 2 to the 12th power, right? You could say that this is somehow 11 cubed times 3 over 2 to the power 12. But it's not clear to me that that actually saves much work. So I'm not entirely sure whether there's a better way to do this. But this approximation is not bad. If I did this, I could actually probably get somewhere. Okay, let's take some other questions. I see that Caden Xia has asked, is MOP not being held either on-site or virtual? I can tell you that the answer is, you may have heard that there's a a new Amy, like the second Amy is happening. There's except there's a new name. I think it's like the AO Amy or something like that. It's the one which happens to have online Amy. And because that's actually happening, we will also have USAMO with probably an extra O inside it somewhere. And then we will have, after that, we will in fact have a Math Olympiad training program. But that will actually not be run in person. That's too dangerous right now. We'll do something which is online. That I don't know if that's been officially announced yet, but we are looking. So if it hasn't been officially announced yet, that's up to the Mathematical Association of America to announce. But what we're thinking about right now is to try to find some way to safely help to train everyone if they are preparing for the International Math Olympiad. Okay. Oh yes, clearly we should give the name of the USAMO the USAMU, because it's got some more onlines and other things inside it. Okay, more questions. Did you gave IMO? I'm not sure if I gave IMO, but I can tell you I took IMO. So maybe my answer is negative, the exact opposite. I did not give IMO. No, I took IMO. Okay, what else can we do? IMU. I guess the International Math Olympiad can be online. So then it should have a new logo. It should be a cow. Okay, what else do we have? Oh, neat. Okay, so one of the organizers of the competition has sent a message in. And this is from Arpit Ranasaria. Arpit Ranasaria says, here's how you actually should do this problem. Let's see. So it is true. I was thinking about trying to do it where you multiply by root 17 minus root 11. But it wasn't clear to me that that would work. So let's see what happens. So normally when you have these pluses with roots, you also want to try minuses with roots. So let's try. Ankit says, let's do this. X is root 17 plus root 11. Y is root 17 minus root 11. Now if we do this, try to solve for x to the 6th plus y to the 6th. Okay, let's see what happens here. If you do x to the 6th plus y to the 6th, a lot of things will cancel, right? And if you have all these things that are canceling because you have some roots which are plus and some roots which are minus, you can indeed figure this out. You can indeed get this. But then the question is, so what? I guess that's the point. Oh, I see. This is actually very clever. Okay, I like it. So let's try to expand these up. What is that noise? There was a helicopter going overhead. Okay, so let's see. Root 17 plus root 11 to the 6th power. This uses what's called the binomial theorem. The binomial theorem goes like this. Let's do x to the power 6. Yeah, thanks, Ankit. You guys are really clever. X to the power 6 is root 17 to the power 6. Plus, by the binomial theorem, it's 1, 6. The next one is 6 choose 1. 6 times root 17 to the power 5 times root 11. The next one is 6 choose 2. 6 choose 2 is 15. Times root 17 to the 4 times root 11 squared. Oh my gosh, it's long. The next one is 6 choose 3. 6 choose 3 is 20. 20 root 17 cubed. Root 11 cubed. And it's running into my head. So that's a cube there. Then it's now plus 15 times root 17 squared. Root 11 to the 4th. Plus 6 times root 17 times root 11 to the 5th. Plus, finally, root 11 to the 6th. Now, what's the point of this? The point of this is that if I do this with y to the 6th, a lot of these are the same, just with minuses. Now I'm going to do something that you should never do in class. Y to the 6th equals all of this where I put minus signs here. Are people seeing what I just did? So the y to the power 6 is the same thing, except that in a few of the places I put minus signs. That last one is hard. This one over here is hard to read. This is a minus sign. Okay, and the reason is because when you do this with negative root 11, it's when root 11 is to an odd power that you put a minus sign. So now let's add them together. Oh, you guys are great. X to the power 6 plus y to the power 6 is now equal to, all this canceling happened. You get 17 cubed. Now the plus and the minus cancels. And look, these are even powers. It's brilliant. Plus 15 times 17 squared times 11. And then plus, over here, 15 times 17 times 11 squared. Plus 11 cubed. So you could figure this out. This is actually not ridiculous. You could actually go and try to multiply all of these things out, add them. And when you're done, if you want to know what is x to the power 6, you just subtract y to the power 6. But how big is y to the power 6? It's small. The key is that x to the power 6 is big. It was the 6-digit number or something. Y to the power 6 is really small. Root 17 is about 4 point something. And root 11 is 3 point something. Does that make sense? Because root 17 is, a little bit more than 4, and this is a little bit more than 3, but more than a little bit more than 3. So when I subtract these two, I actually get an answer, which is, in fact, error times 2. What's wrong? There's an error. Mistake, mistake, mistake. We have a mistake. Let's fix the mistake. I saw an alert. Oh, yes, of course, because it's times 2, times 2. Error times 2. Thank you. So it's 17. When we add them together, we should get 2 of them. Fortunately, the way to solve this is 2 times 2. Thanks, guys. Perfect. 404 error times 2 error. But thanks. It's great to have all of you guys here. You guys are great. Yes, we fixed it. And thank you very much for putting the alert out for the audience. So you could just do this, get that times 2, and look at that. If I take this thing, this is 4 point something minus 3 point something. Yes, good. I figured it out earlier than last time. That's called because I looked at your chat. Sometimes when I'm doing the problems, I don't look at the chat because I'm afraid that you'll tell me the whole answer, and I don't want to have it spoiled. And so why is it times 2? It's because x to the 6th has a root 17 to the 6th. Y to the 6th has another root 17 to the 6th. When I add them together, I get 2 of them. So it should be this times 2. And now when x to the 6th has a plus here, y to the 6th has a minus. You add them, they cancel. So I don't need to do anything with that. This 15 has a plus and a minus. So has a plus and a plus. You join them and you get 2 of them. That's how it works. So that's how this works. And so the answer here, we could actually calculate this. Actually, this is amazing because if I look up here, what's that? Is that really less than 1? Root 17 should be 4 point, just a tiny, tiny bit. Root 11 should be 3 times a little bit more than a tiny bit. So this whole thing should be something which is less than 1, right? This whole piece is less than 1. This is going to be, this is nice. This is going to be 0 point something. You know what happens if you take a number less than 1 and you raise it to the 6th power? Poof! It's almost gone. Actually, this is amazing. This means that you can just calculate this thing out and you'll get an answer which is, if you calculate this whole thing out and you just forget about the y to the 6th, this whole thing is the answer up to plus or minus something almost ridiculously small. So in that case, this is an excellent estimation for the answer. Amazing. Okay, well, in that case, I'll say this just shows how clever these problem makers were. I hope that you guys had as much fun as I did playing with these. I intentionally always do this in a way where I don't try to look at the problems beforehand, so you can see what you would actually do if you were looking at these and trying to figure them out. If I was going to say how hard are these questions, my estimation is that these questions are not quite math counts level. These are in fact quite hard. As you can see, these things required us to think outside the box, not just doing a bunch of calculations. Instead, we were able to see that you can even use these complicated ideas in high school math. If you had fun, I hope that you will come and join us again in a future one of these Ask Math Anything shows. What we always do is we always have me attempting to do problems that people pose. And in general, I don't know the answers to the questions, but this goes and tries to show how somebody would think about all of these problems on the fly. Speaking of fly, sounds like there's another helicopter flying over our head, so you'll have to shelter your ears from that sound. Today's Friday, and since today's Friday, we won't have a normal show until the next Monday. We will still have a show on Monday, even though it's Memorial Day. But if you're interested in our weekend show, we'll have a show tomorrow at 8 o'clock p.m. Eastern Time. That one I'll usually show up with a question in advance, and then we'll do Q&A. And that Q&A over on the weekend one is going to be Q&A about not specific math questions, but questions about like learning math and so on. I hope that you guys all had a good week. I certainly thought that this was a fun way to end this week. Let's all give a big thank you to the organizers of the Mustang Math Tournament for providing these interesting problems for us to discuss. Congratulations to them for organizing a successful math competition. And I hope that all of you, if you enjoyed this, might even think of organizing a math competition for other people in just a few years yourself. I'll see you all next time. Take care.